Hello and welcome back to the Science of Concrete Materials class. This is lecture number 35 of the class, and we are continuing our discussion on the testing of hardened concrete. Last lecture we talked about why we test concrete, and we talked about the compressive strength test. This lecture we will discuss the remaining tests. So the first one is the tensile strength. As you may already know, there is no standard tests, that have been adopted by ASTM to provide a direct measurement of the tensile strength of concrete. The problem, secondary stresses induced through gripping makes the test results difficult either to interpret or reproduce. So that's why the test is not practical. But there exists a recommendation for a direct tension test for concrete by certain professional bodies. But these primarily, they are intended for research rather than for routine control or quality control tests. Okay. As yet, there is not enough experience with this test method for a proper assessment for its usefulness to be actually used as a routine test. As I said, as you can see, what would the direct tension would be done. That's how it would be done. Will be just to grip both sides of some kind of a briquette or a prism, and to apply tension on it and get the results. But like I said, this is really the usefulness of such tests for a direct tension test has not been established as of yet. Okay. There is, however, one common method for estimating the tensile strength of concrete through indirect tension test. Okay. This test, this is the splitting tensile test, which is carried out basically on a standard cylinder, tested on its side, in a what is referred to as diametral compression, as you can see here in this figure. So the element on the vertical diameter shown in this figure, is subjected basically to compression stress and tension stresses. Basically, we apply compression, so basically we will get tension stresses in the transverse direction here. All right. As specified in ASTM C496, the test is carried out on a cylinder specimen, either basically cast cylinders or drilled cores for existing structures. The bearing strips are made of from 3 millimeter wide plywood that is free of imperfection, and it's about 25 millimeter wide. As you can see, this testing strip will be located right here. Okay, so the specimen basically is aligned in the machine, as you can see here in the figure, and the load is applied at a rate of 690 to about 1,380 kilopascals per minute. So the splitting tensile stress, what we applied. The tension stress, is expressed. Of course, we load the cylinder in this arrangement until failure. The tension stress is expressed as follows, as you can see in this equation, okay, which is basically sigma sub t, which is the tensile splitting stress, and the value P is basically the applied compressive load, L is the length of the cylinder, and D is the diameter of the cylinder. Okay. As you know, it is not practical to apply true line load along the top and bottom of the specimen, partly because the sides are not really smooth enough, and partly because this would induce extremely high compressive stresses near the points of the load application. So the load is usually applied, as I said, through a narrow bearing strip of relatively soft material, as I mentioned, as you can see here. All right. The tensile stress distribution along the vertical diameter of the specimen is, after that is established, and it is, basically as shown, the distribution of the stress as shown here in this figure. So that is, there are very high compressive stresses near the ends of the vertical diameter and a nearly uniform tensile stress acting, over about the middle 2/3 of the specimen, as you can see here. This is tensile stress, and we have the compressive stress right here. Okay, so since the concrete is much weaker in tension than in compression, failure will be in split-in tension, at a much lower load than would be required to crush the specimen in compression. So, permitting an estimate to be made for the tensile strength of concrete. All right. Also, just to mention, the stress, this type of stress could be carried out on cube, just so that it's the same principle applied, and the split-in stress also is determined as well. We have to keep in mind, though, that there is no simple relationship between the values of tensile strength found from the split-in test and those measured in a direct tension. Although it is commonly assumed that, split-in tensile strength values are about 5 to 12% higher than the direct tensile strength values. And also, this is not, always true. So you just have to remember that. In addition, some recent studies have shown very little difference between the two values of tensile strength. And, for some concretes, that direct tensile strengths have been found to be slightly higher than the split-in strength, okay? It would appear that the ratio of the direct tensile strength to the split-in tensile strength depends upon the strength level of the concrete and upon the maximum aggregate size. It should also be noted that recent more details analysis of the split-in tension tests have shown that the split-in tensile strength determined, according to these test procedures, should not be considered to be true, material property. It's not a true material property. The results obtained, depend on the specimen size and the width and type of the bearing strips. So it's not really a true material property because it depends on so many variables, all right? So that's the tensile or the split-in cylinder test, okay? The next topic we will discuss is the flexural strength. The flexural strength of concrete can be determined following the procedure of ASTM C78. The specimen is a beam or a prism measuring, 150 by 150 by 500 millimeter long. Typically, the beam is cast where the mold is, filled with in 2 equal layers, each layer being rodded about 60 times, once for each 13 centimeters square of the top surface being filled. Of course, stiffer mixes may be consolidated by vibration, as we specified for the compression test, cylinders for compression tests. So that could be done also the same way. The beams after that, after prepared, after cast and molded and demolded, they are cured in the standard manner as per ASTM recommendations, and then tested in flexure, in third point loading, as you can see in the arrangement here. Okay, this is what I mean by third point loading. The tests also can be done on beams sawn from hardened concrete. So we can basically prepare a specimen with the same dimensions from an existing concrete structure if we need to. Okay, so in order to provide smooth, plane and parallel faces for loading, the cast specimens, when are turned on their sides with respect to their positions, are as molded. So just basically to get smooth, plane surfaces. For some reason, this is not the case. The specimens, must be ground or capped in order to get a plane testing surface. Also, they can be, if that's not possible, they can be shimmed in order just to level them. Many things can be done, but again, you have to. This is a standard test, so the procedure of ASTM have to be followed exactly. After that, the specimens are loaded at a rate of 860 to 1200 kilopascal per minute, as in this arrangement, as you can see. Then the theoretical maximum tensile strength, or what is referred to as modulus of rupture, R or F prime R, that's the modulus of rupture, is then calculated from the simple beam bending formula for third point loading. Okay, remember that. The modulus of rupture, or R, will be equal to P times L over BD squared. P is the maximum total load indicated, L is the span length of the beam, B is the specimen, the beam width, and D is the beam depth. This equation right here holds only for if the beam breaks between the two interior loading points, meaning approximately in the middle third of the beam. On the other hand, if the beam breaks outside these points by not more than 5% of the span length, then we have a second equation that we use to calculate the modulus of rupture, as you can see here in the second equation, which is R equal to 3 times P A over BD squared. Okay, A is the average distance between the point of fracture and the nearest support. Okay. One thing we need to remember, however, that this test tends to overestimate the true tensile strength by about 50%, largely due to the fact that the simple flexure formula, according to this equation right here, assumes that the stress varies linearly across the section or the cross section of the beam. But, because the concrete has a nonlinear stress-strain curve, this assumption is not true, as we know. So the stress block at near failure particularly is more nearly parabolic than triangular, as shown in this case. So that's why, the assumption of it as being linear tend to overestimate the strength. This is actually the true distribution of stress in reality, and this is the assumed stress distribution. That's why the overestimation occurs. However, the test remains very useful since, concrete members tend to be loaded in bending rather than in axial tension. And so the values obtained from a flexure test are better representation of the concrete property that is of interest. So that's why it is actually useful. So it is also possible to carry out flexure tests on, in a center point loading, as described in ASTM C293. ASTM C293. This test method is not as good as the third point loading, and also it is not a substitute for it. I mean, we could carry out that test, but it will not substitute the third point loading, okay? Also, what I have to say about the test results or the tensile strength of concrete, as in the case of the compression test, the test parameters can greatly affect the observed strength, okay? In particular, the size of the sample effect and the other factors we talked about. And again, doing the test, I mean, consistency when comparing the results and making sure our results are reproducible, all this, make us feel comfortable that, the results we are getting are basically reasonable, okay? Okay, so that's about the flexure test. Next topic is the modulus of elasticity. As we have seen in detail in the previous lectures, the previous modules, the stress-strain curve for concrete is not linear. I mean, we know that, we have established that. But to calculate the stiffness or basically the expected deflection of structural members, it is still necessary that some estimation of the modulus of elasticity is obtained. It is possible to define the modulus of elasticity in a variety of ways for materials with nonlinear stress-strain curves, as we explained before. The most common way for concrete is to measure the chord modulus of elasticity, or E sub C, as we talked about before. This is done using the method outlined in ASTM C469. Okay, a typical setup is shown here. I'll talk about it in a minute. Okay, so basically what we do here, we take a standard cylindrical specimen, to which we attach a compressometer, as seen here. Of course, this compressometer is, attached to the side of the specimen. Then the specimen is loaded and unloaded, primarily to properly seat the strain gauges. It is then loaded slowly at a stress rate of about 241 plus or minus 34 kilopascal per second, okay? In compression, of course, and a stress-strain curve is drawn, all right? The chord modulus of elasticity is calculated using this expression right here. So basically, it's the chord modulus equals S2 minus S1 over epsilon 2 minus 5 times 10 to the minus 6, okay? So what are these terms? S2 is the stress corresponding to 40% of the ultimate load. S1 is the stress corresponding to a longitudinal strain, E1, which is equal to 50 microstrains, or 50 times 10 to the minus 6, okay? And epsilon sub 2, basically the longitudinal strain produced by the stress S2. Okay, simple and straightforward. So, and again, this is the setup. As you can see, the compressometers, are attached to the side of the specimen right here, and they attach, to monitor their values. Okay, so from the same test, though, we can calculate the Poisson's ratio, or otherwise referred to by the simple nu, as you can see from this formula right here, which is epsilon sub T2 minus epsilon sub T1 over epsilon sub 2 minus the 50 times 10 to the minus 6. And again, the epsilon sub T2 and epsilon sub T1 are the transverse strains at mid-height of the specimen produced by the stresses S2 and S1 respectively, okay? Also, we can calculate the modulus of elasticity in shear, G, which is basically obtained. We cannot obtain this value by direct measurement, but we can calculate it from this relationship, as you can see, which is the shear modulus equals the elastic modulus divided by 2 times 1 plus the Poisson's ratio, okay? Also, we can determine the dynamic modulus of elasticity. So it is often desirable to have some non-destructive test for the stiffness of concrete specimens, so that, the reason for this, maybe we can, the progressive changes in material due to sustained chemical attack, for example, or repeated freeze and thaw cycles, agent, or other factors that affect concrete. So we can progressively measure the modulus of elasticity over time to see how the concrete is being affected or is being damaged. So for this purpose, the dynamic modulus of elasticity measurements are very convenient, since they are non-destructive and since there is also a general, but although empirical, relationship between the modulus of elasticity and the compressive strength. So it serves many purposes, really. So the standard way of carrying out these tests is to measure the dynamic modulus of elasticity, or referred to as E sub D, by vibration of concrete specimens at their natural frequency. So the method is described in detail in ASTM C215 using one of the test setups shown schematically here, okay? So basically what we're looking at here, a test specimen, either a cylinder or a prism, is supported at its nodal point or points, so that it may undergo free vibration without significant restrictions. Meaning, for transverse vibration, as you can see here, it is supported at points, 0.224 of its length from each end, as you can see here. Okay. For longitudinal or torsional vibration, it is supported at its center, as you can see in these two figures. So the driver or impactor and pickup unit are placed as shown in the figure here, okay? So that's how you arrange the driver and the pickup points. These are, photos showing these impact resonance apparatus for, transverse setup and for longitudinal setup. That's basically this and one of these tests, okay? So using the forced resonance test, for example, this setup right here, the specimen is then, forced to vibrate at the various frequencies. The frequency of vibration that gives the maximum output indicates the fundamental frequency. When using the impact resonance test, I'm sorry, let me go back. This one here, this is the setup for the impact resonance, okay? The specimen is struck and its response monitored using a lightweight accelerometer. The fundamental frequency is measured using, a waveform analyzer or frequency counter, some of these devices, okay? For comparison, you have to keep in mind, for comparison, all specimens should be analyzed using the same test method. We cannot mix and match. That's something you have to keep in mind, okay? So the dynamic elastic modulus, E sub D, can be calculated from either the transverse or longitudinal frequency using the general expression shown here, which is E sub d equals k times m n squared. M is the mass of the specimen in kilograms, n is the fundamental frequency of vibration in hertz, and k is a constant which depends on the type of vibration, transverse or longitudinal, and depends also on the specimen dimensions and the specimen shape. Okay? Similarly, though, the dynamic shear modulus, G sub d, is obtained from the expression shown here, which is equal to B times m n squared. B is the constant dependent on the shape and size of the specimen. The ASTM C215 basically gives formulas for the calculation of K and B for various specimen geometries, if you need to actually refer to that. So these are straightforward equations. And again, you know, consistency and accuracy in carrying out these tests are key. So the person who should be the same person should carry the tests on all specimens to be compared to each other, and also the person should be really familiar with the apparatus and how it is set up and how the values are read. Okay. Also, the dynamic Poisson's ratio, nu sub d, can be obtained, as you can see from this equation right here. Okay. So these are really very convenient methods, although we're talking about these values may not be of 100% accuracy, but for comparison reasons, especially with other test results, they are very good. So in general, the dynamic elastic modulus determined in this way will be considerably higher than the static modulus of elasticity, since, you know, the dynamic modulus is approximately equal to the initial tangent modulus. Refer back to those lectures in the previous module, rather than the chord modulus, which is defined by ASTM C469. Okay, so familiarity with these terms, familiarity with these instruments and apparatus is key to use in these basically this setup. Okay. The last subject I'm going to discuss here is the non-destructive testing. Okay. A great deal of work has been done since maybe the late 1940s to try basically to develop rapid non-destructive tests that would provide a reproducible measure of the quality of concrete in a structure. Many such tests have been, you know, proposed, but they still lead to difficulties in interpretation of the results. Okay, so while the development of a highly reliable in situ test to monitor concrete qualities remains an elusive goal, some of the tests actually are useful for several reasons. First, they can be used as a quality control measure. Second, they can help determine the time maybe for form removal. And third, they can help in the assessment of the soundness of concrete in existing structures, meaning after a structure has been damaged maybe by fire or by any other means. Okay, so those are good as, you know, first estimates to try to gauge the strength of concrete in an existing structure, especially, as I said, after an event like fire or something like that. However, it must be remembered that, you know, the tests described subsequently here do not measure the concrete strength. Rather, they attempt to provide an estimate of the concrete strength through correlation with some other property. All right, again, you have to understand that. Unfortunately, though, as it is usually the case in concrete testing, all of these non-destructive tests give results that are affected by a number of parameters, such as aggregate type and size, age, moisture content, mixed proportions, and other variables. So again, we have to be aware of that. So the correlation between the measured property and strength is different for different concretes and must be determined for the particular concrete in question. These tests, are useful primarily for indicating differences in concrete quality from one part of a structure to another. As I said, comparison. So they may indicate those portions of the structures that maybe require much closer examination, which will usually involve the drilling of some cores and possibly petrographic or other type of examination. Okay, so they are good for first estimation and for comparison purposes. The available non-destructive in situ tests can be classified in a number of different categories. Only a few tests have been adopted as ASTM standards, but this still does not imply that the tests listed in ASTM are in any way better or more accurate than the other tests available. So sometimes judgment and experience and particular knowledge with certain methodology is key to determining what and convincing people which methodology to use to assess a structure. It is, as I said, being accepted or listed as an ASTM standard does not mean this test is better than others available. It simply indicates that the new tests that are available are being developed more rapidly than the rate at which the standards can be proposed or adopted by ASTM or other standards bodies. So, and again, does not mean if a test is not being standard by ASTM, that does not mean you as a professional or a specialist, does not mean you cannot convince people to use this test if you have the knowledge and the expertise how to use it and interpret and present the results. Okay, so probably the most common non-destructive test is the rebound test using a Schmidt rebound hammer. I'm sure many of you heard of this. This device, as I will show here, was developed in 1948, okay, and it is universally used because of its simplicity. The test measures the rebound of a hardened steel hammer impacted on the concrete by spring, basically. So although there is no theoretical relationship, okay, empirical correlations between rebound hardness and strength can be obtained, as you will see on this figure here. Okay, so this method is described in detail in ASTM C805. So it is worth reading though. Okay. So as I said, this is the hammer. Basically, this is a detail, and this is a cross section in the hammer, and it shows all its components involved in the testing. Sorry, go back here. All right. This is here a calibration chart for concrete, made with crushed limestone, natural sand aggregates. This particular concrete we are doing the calibration for. Okay, you have to be aware certain adjustments have to be made, depending, for example, on the position, because, for example, the calibration was done either in the horizontal or in the vertical. So whenever you vary from that calibrated position, you have to make certain adjustments. Also, whether, based on the moisture condition, whether it's dry or an SSD condition, all this have to be taken into consideration. It's not really easy to calibrate this device for a certain concrete, but it has to be calibrated for that certain concrete. You have to establish a certain correlation or a relationship between the values you get from that rebound hammer, the readings, and the strength of the concrete. Okay, if I do not see such a calibration curve, I will basically discard the results. Okay, so that's something you have to keep in mind. Here is a photo. Like I said, really, it's a simple device. I have used it. It's very convenient. And again, it's an excellent device for a first estimate, given you know what you're doing, okay? Okay, so the results of the rebound hammer will be affected by the following parameters, as we said. First, the surface finish of the concrete being tested. Troweled surfaces, give higher values than formed surfaces. And ground and unground surfaces cannot be compared. Keep that in mind. When comparing, it has to be extremely accurate. Second is the moisture content of the concrete. Dry concrete gives higher values than does wet concrete, okay? Temperature. Frozen concrete will give very high values and must be thawed before testing. The temperature of the hammer will also affect the rebound number. Keep that in mind. The rigidity of the member. Stiffer or more rigid members will give higher readings. Okay? Carbonation. If the concrete has been subject to carbonation. Carbonation on the surface can increase the hardness values by as much as 50%. Okay? The direction of impact. The orientation of the hammer, upward, downward, horizontally, or at an angle, all affect the reading, since gravity affects how far the hammer mass will move. Okay? So, as I said, this is basically what you do. The hammer it bounces. You impact the hammer on a concrete surface. You get a reading, and from a calibration chart, you get the concrete strength. So all what we have listed here will affect the readings. Okay, so again, accuracy and thorough knowledge of this method is required for anybody to attempt using it and interpret the results. Okay, so the general view held by many users of the Schmidt rebound hammer is that it is useful in checking, as I said, the uniformity of concrete and in comparing one concrete against another, but that it can only be used to obtain rough indication of the concrete strength in absolute terms. Okay? So that you have to keep that in mind. It's not an exact reading. The rebound hammer will not, if the rebound hammer, based on the calibration chart, give me the concrete, for example, 20 MPa or whatever value is, that does not mean it is absolutely that. Okay, we are using it in comparison with other specimens of the same structure or similar conditions or whatever, but it's not an absolute value. Keep that in mind. Okay, the next test we will talk about is the penetration test, or penetration resistance rather. This type of test involves measurement of the resistance of concrete to penetration by a steel probe driven by a given amount of energy. This is described in ASTM C803. The most common device for this type is the Windsor probe. This is a schematic of it here, and these are some photos of some of the available devices basically. Okay? So it consists of a powder activated driving unit that basically fires a probe into the concrete. The depth of penetration, or in a practical or operational manner, the exposed probe length is measured, and this can be correlated with strength. Since in this technique there is considerable penetration into the concrete, surface texture and carbonation have less effect than in the rebound hammer case we discussed previously. But mixed proportions and materials properties are still important, and the device must be calibrated for the material in question. Okay? For example, harder aggregates tend to give higher apparent compressive strength. So, okay, we cannot go compare two concretes. of different properties, different material mix of proportions, different aggregate types and everything. You cannot. Comparison has to be consistent and on level basis, basically. Okay, so this is like a simple test. I have used it actually when investigation exists in a structure. Sometimes you get to use all these non-destructive methodologies in order basically to get an idea of the type, the quality of the existing concrete. But all this will not be substitute for eventually doing, for example, drilled cores and testing them, or doing petrographic examination, or sometimes even chemical analysis we've done. But those are, if you become familiar with them, know how to interpret their results, they're excellent starting tools to basically steer you in the right direction. I mean, I'm not warning you not to use them, but when you use them, make sure you know how to use them. That's all I'm saying. Okay, the next test basically is the pull-out test. Pull-out tests involve the determination of the force required to pull a steel insert out of concrete in which it was either embedded during casting, like a casting anchor, or an anchor or an insert that has been installed after casting, a post-installed insert, okay? A suitable apparatus for this is described in ASTM C900. I recommend you read that and become familiar with it, okay? So the arrangement is as this, this figure here shows the arrangement for a casting insert. Something is cast during the placement of concrete. And sometimes we do not have a casting insert because nobody thought about that we are going to need to determine the pull-out capacity of the concrete 2 years later. So we will end up, for example, drilling and installing this type of insert with this expansion tool in order to make it, for example, to arrange it in a way to bear at the concrete when it's pulled out. Okay. So basically these are the setup. This is the cast-in, this is the post-installed. So how we measure the pull-out strength. So assuming that the failure surface is basically a frustrum as shown here, like this. The nominal stress at pull-out, which is referred to as F sub n, can be calculated using the equations right here, okay? So this is the equation, P over A times sine alpha, basically D3 minus D2 over 2S. A, which is an area basically, which is here, the fracture surface area. Alpha is half the frustrum apex angle, which is the arctan, equals to D3 minus D2 over 2H. P is the pull-out force, evidently. F sub n is the nominal normal stress in MPa. Okay, S is calculated using this equation. D2 is the diameter of the pull-out insert head. These values are actually all defined here, so you refer to this graph. D3 is the inside diameter of the bearing rim, right here. This is the bearing ring right here. Okay, H is the height of the conic frustum in millimeter. S basically the slant height of the frustum in millimeter. Okay, so all these values as actually indicated on this schematic right here. Okay, so basically certain computation that you have to do in order to arrive at this value. Okay, and then we will calculate the F sub n. Okay, So essentially, this provides some measure of the shear strength of concrete. And this actually can, for any particular system, be correlated with compressive strength, okay? The test is really economical and rapid, although it does leave a hole in the concrete that must be repaired, but this is really not a big deal. It is probably better than those discussed previously. So this is a good test because, you know, at a greater depth and volume of concrete are tested in this case. The cast in place test, you know, of course, must be planned in advance. If we are planning, for example, to measure such tests, we can do it. If it was not planned or something that, you know, came up later, then we have to use the post-installed anchor, and it can be done easily, quickly, and efficiently. So this is again, as I said, this is really a good test, and I have used it on many occasions, and the results can be very useful. Okay, so this is the test that I recommend you become familiar with. Okay, the next topic is the ultrasonic pulse velocity. This method is based on the fact that the pulse velocity V of a compressional wave in a concrete body may be related to the elastic properties by this expression right here. Okay, so basically V equals to E sub D, which is the dynamic modulus of elasticity, times -1 minus nu sub D, which is the dynamic Poisson's ratio, over rho times 1 plus nu sub D times 1 minus 2 times nu sub D. Okay, rho is the density, the nu is the dynamic Poisson's ratio, and E sub D is the dynamic modulus of elasticity. Okay, so this is a schematic for the apparatus, how it is used, and these are the arrangements for the different tests. This is basically the direct tests. This is the semi-direct, you know, where the transmitting and receiving transducers are located, and this is the indirect surface test. Okay, both are on the surface, but this is the direct test. Actually, this is the most efficient. Okay. Okay, since the pulse velocity depends, you know, only, remember this, on the elastic properties of the material and not on the geometry. So this is a very convenient technique for evaluating concrete quality. Has nothing to do with geometry, it's related to the elastic properties of the concrete. So in a sense, an apparatus such as, you know, the one shown schematically here basically is used to determine the pulse velocity through a known thickness of concrete using the procedures, you know, outlined in ASTM C597. A number of commercial devices are available that, you know, meet these requirements with basically an accuracy of measurement of about ±1%. So there are very accurate testing machines that are available in the market, and they are very good though. In fact, mechanical impulses, you know, applied to a material, generate three types of waves: longitudinal or compressional waves, shear or transverse waves, and the surface, or otherwise referred to as Rayleigh waves. The longitudinal waves are the fastest, okay, and they are the ones that are most useful for testing purposes. So the pulse velocity may be used directly as a quality control measure, but more commonly it is correlated with strength. So pulse velocity can be measured in several configurations, you know, as shown right here, okay. Although, as I said, the method shown right here, the direct method, is the one, you know, that gives the best results. Okay, but the other two available, and again, knowing how to interpret the results is key. Okay. So, as with everything else, that pulse velocity is affected by a number of factors. Okay, first, the contact surface smoothness. If the surfaces are not reasonably smooth, they should be ground smooth. A coupling medium such as maybe grease must be also used to ensure good contact between the transducers and the concrete. The path length. The pulse velocity seems to depend on the path length, decreasing somewhat as the path length is increased. And again, all this you have to be aware of and compare apples to apples when you compare. Temperature. The pulse velocity is not sensitive to temperature in the range of 5 to 30 degrees Celsius. At higher temperatures, the pulse velocity is decreased. At temperatures below freezing, it's increased. Keep that in mind. Moisture content also. Pulse velocity increases with increased moisture content. The reinforcing steel, the presence of steel bars will tend to increase the pulse velocity, okay? Also the concrete strength, for a given compressive strength, the pulse velocity is lower for older concrete than it is, for newer concretes, okay? Anyway, in spite of these difficulties I just named, pulse velocity measurements are used regularly as means of assessing concrete quality. They are used to study uniformity or for quality control, estimations of strength, setting characteristics, durability, and the extent of cracking in a member, as well as to determine the modulus of elasticity. I used it extensively in my work and in my research, and I said it's a great tool. And again, as long as you're careful when you apply and interpret the results, I think you'll be fine. Okay? By this, we come to the end of lecture number 35 and also the end of the testing of the hardened concrete module. Next time, we're going to start on the next module of the class, which I believe is the dimensional stability. Okay? Until then, I thank you for watching, and I will see you next time. Thank you.